What you see on the screen is a display of the Waveforms software for the Analog Discovery 2. On the left is channel 1 and channel 2, and I'll explain what those curves mean here in a minute. And on the right is an XY display of what you see on the left. In other words, one channel is the X and one channel is the Y. So what do we have over here? Well, what we have is an increasing series of pulses that are generated by a 3904 transistor. Similarly, down here you see a decreasing train of pulses. What you're looking at is the collector to emitter voltage and the collector current of a 2N3904. Let me try to explain it a little better over here. You'll see at the bottom that this is the 0-volt line, and over to the right is 14 volts. Now, those of you that watched my number 179 on turning the Analog Discovery into a curve tracer may recognize this display because that's what we have here, but you may say, well, how in the world can you get 14 volts out of an Analog Discovery 2? And I'll show you that answer in a minute, because ever since my 179, I have wondered if there might be a way to increase the collector to emitter voltage so that you can get a more accurate display of the characteristics of a transistor like a 3904, which is designed to operate at considerably more voltage than the Analog Discovery can generate. So I was watching my number 179. I don't normally do that, but I was watching it the other day just because I had YouTube on, and the one I was watching finished, and it auto-played my number 179. I was actually watching a video by Alan, W2 AEW, and one of mine came up next, and I was just sort of sitting there zoned out, and got to the part in that video where I speculated that, gee, it sure would be nice if you could get a much higher voltage out. And then a thought occurred to me, and I'll show you what that thought is here in a second. Basically, what I have done is I have extended the use of the Analog Discovery to much higher voltages. Now, I deliberately have limited, in this case, the maximum voltage to 20 volts because that is about all that the Analog Discovery can handle, at least the first Analog Discovery 1. Now, the Analog Discovery 2 is rated out to 25 volts. But just to be safe, I have used some larger resistors because the idea here is just to prove concept. Someone who wants to drive transistors out to 20 or 25 volts of collector voltage is certainly welcome to do so, but they may have to readjust some of the resistors that I'm using. Actually, what this circuit consists of is a diode and 2 resistors. So let me show you that. Here is a sketch of the circuit. For those of you that are familiar with my earlier videos on the subject, some time ago I did a curve tracer, which was more just a proof of concept. In this one, what I had done is I had generated a series of stair steps out of Waveform Generator 1 and applied those to a base limiting resistor to the base of a transistor. So basically the stair steps work through the base resistor to the emitter, and of course back to Waveform Generator 1. And then what I had done is connected Waveform Generator 2 between this point and this point, and had adjusted it so that it generated a triangle wave that would, in essence, sweep the collector voltage. And then I put a resistor in series with the collector so that I could develop a voltage proportional to the collector current. So channel 1 measured the collector voltage and channel 2 the collector current. Now I have shown here a 50 ohm resistor, but I'm actually using a 1K resistor right now, largely to limit the current through this circuit to keep everything within limits. So what's different? Well, instead of the waveform generator directly coupled to the transistor, it occurred to me that if I used a transformer, that would isolate this voltage from this voltage. So what I am using here is a filament transformer connected backwards. On this side, I have waveform 2, and it's generating a triangle wave, which is inductively coupled into this side. I put the diode in to make sure that only the polarity that would cause conduction in the transistor would occur. It's more just a safety feature. Whenever you're using inductors, it's a good idea to make sure that you have some kind of device that prevents things like inductive kick from destroying the transistor. So, this is the basic circuit. Now let me show it to you on the breadboard. Here is the breadboard. The wires you see extending off to the left here are coming from the Analog Discovery 2, and then I have it connected to this little breakout board that you can buy from Digilent. You don't need to have this board. You can just connect the wires from the Analog Discovery 2 directly to this, but it makes it convenient because it has all the pinouts right there in front of you. Then the base resistor is right here. That's the 100K that's going to the base, and the transistor, let me zoom in a little bit. You might be able to see a little better. The transistor is right back there, and then this is the 1K collector resistor going over, and you'll see there's a diode connected to a transformer. And what that is a 12-volt filament transformer connected backwards. In other words, I'm driving what is normally the secondary, the 12-volt winding, and taking the voltage out of what would normally be the primary. So in other words, instead of a 10-to-1 step-down transformer, I'm using it as a 1-to-10 step-up transformer. So for every volt that the Analog Discovery generates, this transformer generates 10 volts. And then I adjusted the Analog Discovery's waveform generator output to produce about 20 volts. Now, when you load everything down with the circuit, that 20 volts drops to about 14 volts, but you could go higher than that. I'm nowhere near the limits of the waveform generator. But you do want to be careful because the inputs to the Analog Discovery are only rated at plus and minus 25 volts. So you don't really want to go much over 20 volts unless you know what you're doing, because you don't want to blow up your Analog Discovery. You could, of course, put a resistor divider in the collector voltage circuit so that you were, for example, taking half the voltage and then just multiply it in your mind in the Analog Discovery. So what I'm saying is, you could, for example, drive this to 40 volts by using 4 volts out of the waveform generator. That would then give you approximately 40 volts out of the transformer. And then if you divided that by 2, say with the resistor divider, you'd be back to 20 volts. But then on your display, you'd want to be sure to remember that you have the divider in there. when you're doing or plotting the collector emitter characteristics. Okay, let's go back now and look at the actual waveform generator and what is going on, as well as the display on the output. And then I'm going to kind of wrap this up, but I will say that I'm very pleased that this experiment worked, because it's something I wanted to do for quite some time. Here is the waveform generator for the Analog Discovery 2. Channel 1 of the waveform generator is generating this step pulse, which if you, or step voltage, which if you watched my number 179, you already know, and it explains in there how I generated this stair step and so on. What this does is it provides first 0 base current, then a step up in base current, a little bit higher base current, a third level, and finally a fourth, or you might call it a fifth level if you count 0. So basically, depending on the size of the base resistor you use, because remember this is voltage, that converts into a certain current. 0 current, a little bit of current, a little more, a bit more, and the maximum that your base resistor will allow. Then waveform generator 2, or channel 2, is generating this triangle wave, which basically is used to sweep the collector of the transistor. So as I pointed out in 179, one reason that the Analog Discovery behaves very well in this kind of environment is because you can link these two together. And the I don't know if you can, yeah, you probably should be able to see it up here. It shows that the channels are synchronized. I won't talk any more about that here. Go back to 179 if you want more on that. So this is what the waveform generator is doing. Now let's look once again at what the scope is showing. Once again, we have on the left is the scope, and for those of you that would might like to know what the readings are, the time base is set to 10 milliseconds per division. I have offset the trigger point to the far left of the screen, mainly so that this train of pulses starts with the tallest pulse and goes to the right. And channel 1 is set to a minus 10 volt offset with 2 volts per division. Channel 2 is set to a 3 volt offset with 1 volt per division. And as you see, 14 volts is here. So that is the sweep with 0 base current. Then each of these is a successively higher base current. And of course, if I lowered the size of the base resistor, this would move up. All of these would move up. The 0 would stay where it is. So you can basically, suppose you wanted a very even spacing here, you could lower the base resistor to increase the current, and that would move this line up, and then all the others would move up proportionally. So what you see here is an improvement to the Analog Discovery 2 used as a curve tracer. And as I pointed out earlier, you could use even higher voltages than this, being careful to not exceed the input capabilities of the Analog Discovery's oscilloscope. Now, this technique of using a transformer to, in essence, multiply the output of the Analog Discovery 2, I think might be useful in some other applications as well. For example, some people have wondered whether you could use the Analog Discovery 2 in tube circuits. And the answer, I think, is yes, if you know what you're doing. You might be able to use a step-up transformer in this sort of application to drive, say, a tube circuit that requires more than 5 volts of drive. Now, the Analog Discovery 2 wasn't designed for that. It really was intended to be used in 3 and 5 volt logic. So you do need to be careful, and you do need to be aware of some of the downfalls of using inductors. Fast switch inductors can generate incredible voltages, thousands, in some cases tens of thousands of volts. So don't take it lightly, but if you know what you're doing, this sort of thing might be trigger some thoughts among the viewers, and who knows what they might produce. At any rate, I thought you might be interested in seeing an improved curve tracer, in this case for a 2N3904, driving the collector to 14 volts, which is about 3 times what you normally can get out of the, normally right here, about 5 volts is the most you can get out of the analog discovery. So we're getting about a 3-to-1 increase. And understand, if we drove the waveform generator and the transformer harder, we could produce a lot more voltage than this. In fact, with a 10-to-1 step up and a 5-volt peak, you could get up to 50 volts out of the transformer. The trouble is that would exceed the input ratings of the oscilloscope, so you need to take care of that perhaps with a resistor divider or something. At any rate, I was pleased that this experiment worked out. Often when I get ideas like that, and sitting on the couch watching YouTube, they don't turn out as well as this one did. But I hope you've enjoyed this. You might want to try constructing a curve tracer of this type. So for those people, I'm going to show the schematic one more time and then wrap up this video. Here once again is the schematic. Waveform 2 into the 12 volt, I'll write it here, winding. The output, which is the 120 volt primary, driven through a diode to provide the collector to emitter voltage for this transistor. A 100K base resistor to waveform 1. A 1K, I've changed that. I started out using 50 ohms and it didn't really work as well. Though the lower this resistor, the more accurate your readings are in terms of measuring, because remember that any voltage dropped across this resistor is not voltage that's left for the collector to emitter. So if you want to drive the collector to the highest possible voltage, you want this to be the lowest resistor that is usable in this circuit. So you might want to lower this to 500 ohms or 100 ohms or maybe even down to 50 ohms. But nonetheless, you do need some sort of resistor here in order to sense the current through the transistor. And then of course channel 2 and channel 1 with the plus terminals tied together, and I just did that for convenience. They could be reversed. And then channel 1 reads is tied to the emitter. Channel 2 reads the sweep voltage, the sweep current, and channel 1 reads the collector to emitter voltage. So a nice little improvement to the analog Discovery 2 used as a curve tracer. I hope that you've enjoyed this, and whether you decide to build a curve tracer or you just suddenly remembered that, oh yeah, I guess I had thought of some things that where I might be able to use a transformer either in its forward or reverse configuration, because remember, a transformer is just 2 windings with some kind of magnetic material in between, whether that's air or iron or whatever. And so as long as you stay within the frequency range of the transformer you're using, hooking it up forward or backward is not a problem. But I will caution everyone, please do not try to use these sorts of transformers backwards on the AC line. They will blow up. The secondary of a filament transformer is not designed to be connected to the AC line. The primary is. So just because you see it backwards here, that's because we're driving it out of a high impedance generator. If you tried to hook this to an AC line and say, well, I'll just use AC because I don't have an analog Discovery, you will blow up your transformer, you could blow up your house, and who knows, it could be even worse for you. So definitely do not try to connect this to the AC line. Well, with that caveat, I thank you for watching the video, and I hope you got something out of it. I certainly enjoyed making it, and looking forward to some future projects. In the meantime, please have a nice day.